Welcome to our comprehensive guide on microcontrollers and microprocessors, the heart of modern embedded systems. In this video, we'll explore the fundamental differences between these two essential components, their architecture, and how they power everything from smart devices to industrial automation. Whether you're a beginner or looking to refresh your knowledge, this journey will clarify key concepts, introduce you to popular development boards, and walk you through practical programming basics. Let's start by understanding what embedded systems are and why they matter in today's technology-driven world. Microcontrollers and microprocessors are often confused, but they serve distinct roles in electronics. A microcontroller (MCU) is an all-in-one chip with CPU, memory, and input-output ports designed for specific control tasks. In contrast, a microprocessor (CPU) focuses on high-speed data processing and relies on external components for memory and I/O. MCUs are ideal for embedded applications like appliances and sensors, while CPUs power computers and complex systems. Understanding their differences helps you choose the right component for your project. Let's dive into the architecture of a typical microcontroller. An MCU integrates a central processing unit, memory blocks, and a variety of input-output ports on a single chip. This compact design enables efficient control over hardware devices. The architecture is optimized for real-time operations, making MCUs perfect for tasks that require immediate response, such as controlling motors or reading sensor data. This integration also reduces cost and power consumption, which is crucial for battery-powered devices. Microcontrollers' core components include the CPU, volatile memory, RAM, non-volatile memory flash, and various I/O ports. The CPU executes instructions and processes data, while RAM temporarily stores data during operation. Flash memory retains program code even when powered off. I/O ports connect the MCU to the outside world, enabling interaction with sensors, actuators, and other devices. Additional peripherals like timers, PWM modules, and ADCs extend the MCU's capabilities for advanced applications. When it comes to hands-on learning and prototyping, development boards like Arduino and STM32 Nucleo are widely used. These platforms offer user-friendly environments, extensive libraries, and strong community support. Arduino is perfect for beginners, while STM32 Nucleo provides advanced features for complex projects. Both boards allow you to experiment with sensors, actuators, and communication protocols, making them invaluable tools for embedded system development. Programming microcontrollers often involves embedded C, a language tailored for hardware control. Embedded C provides direct access to hardware registers, enabling precise manipulation of pins and peripherals. It's essential to understand data types, control structures, and how to interface with hardware components. Mastering embedded C lays the foundation for developing reliable and efficient embedded applications, from simple LED blinkers to complex automation systems. General-purpose input-output (GPIO) pins are the primary interface between a microcontroller and external devices. GPIO programming involves configuring pins as inputs or outputs, reading sensor values, and controlling actuators. Understanding how to set pin modes, debounce switches, and manage pull-up or pull-down resistors is crucial for reliable hardware interaction. Mastery of GPIO principles ensures your embedded system responds accurately to real-world events. Microcontrollers come equipped with various peripherals, such as timers, analog-to-digital converters (ADC), and pulse-width modulation (PWM) modules. Managing these peripherals allows you to generate precise delays, measure analog signals, and control devices like motors and LEDs. Efficient peripheral management is key to building responsive and feature-rich embedded applications, enabling your system to interact seamlessly with the environment. Let's look at some example code snippets that demonstrate basic embedded programming concepts. You'll see how to initialize GPIO pins, configure timers, and read sensor data. These examples provide a practical foundation for building your own embedded projects. By studying and modifying these snippets, you'll gain confidence in writing efficient and reliable code for microcontrollers. UART, or Universal Asynchronous Receiver Transmitter, is a widely used serial communication standard in embedded systems. It enables devices to exchange data over RX and TX lines, supporting wireless and wired communication. UART is simple to implement and ideal for connecting microcontrollers to modules like Bluetooth or GPS. Understanding UART is essential for building systems that require reliable data transfer between components. I2C, or Inter-Integrated Circuit, is a multi-master, multi-slave bus protocol used for communication between microcontrollers and peripherals. It uses just two lines, SCL clock and SDA data, to connect multiple devices. I2C is perfect for sensor networks and memory chips, offering flexibility and scalability. Mastering I2C allows you to expand your embedded system's capabilities with minimal wiring. SPI, or Serial Peripheral Interface, is a synchronous communication protocol that uses separate lines for clock, data in, data out, and chip select. SPI is known for its high-speed data transfer and is commonly used for connecting microcontrollers to displays, memory cards, and sensors. Its straightforward design makes it a favorite for applications requiring fast, reliable communication. Embedded systems often interface with a variety of sensors and devices. These include temperature sensors, light sensors, and actuators like motors or relays. By integrating these components, microcontrollers can monitor environmental conditions, automate processes, and provide real-time feedback. Understanding how to connect and program these devices is crucial for building practical embedded solutions. Smart Monitoring System combines sensors, microcontrollers, and communication protocols to collect and analyze data. For example, integrating temperature and light sensors with a microcontroller allows real-time monitoring of environmental conditions. Data can be transferred using UART and results displayed on an LCD. Such systems are widely used in home automation, industrial monitoring, and smart agriculture. Electronics form the backbone of embedded systems. Understanding basic electronic components and their functions is essential for designing and troubleshooting embedded hardware. From resistors and capacitors to diodes and LEDs, each component plays a specific role in circuit operation. A solid grasp of electronics ensures your embedded projects are reliable and efficient. Capacitors are essential in embedded circuits for storing and releasing electrical energy. They help smooth voltage fluctuations, filter noise, and provide power during brief interruptions. Understanding how to select and use capacitors is crucial for stable circuit operation, especially in systems sensitive to power variations. Resistors limit current flow and divide voltage, making them fundamental for protecting components and setting circuit parameters. Inductors, on the other hand, store energy in magnetic fields and are used in filters and power supplies. Both components are vital for ensuring your embedded system operates within safe and efficient parameters. Diodes control the direction of current flow, protecting circuits from reverse voltage. LEDs or light-emitting diodes are used for visual indicators and displays. Both components are widely used in embedded systems for signaling, protection, and user interaction. Knowing how to integrate diodes and LEDs enhances your system's functionality and reliability. Ohm's law is a fundamental principle in electronics, defining the relationship between voltage, current, and resistance. By applying Ohm's law, you can calculate the values needed for resistors and other components in your circuit. This knowledge is essential for designing safe and efficient embedded systems, ensuring each component operates within its limits. Understanding the difference between series and parallel circuits is crucial for embedded hardware design. Series circuits have components connected end-to-end, sharing the same current. Parallel circuits connect components across the same voltage, allowing independent operation. Each configuration has unique characteristics and applications, from simple LED arrays to complex sensor networks. Logic gates are the building blocks of digital circuits. They perform logical operations on binary inputs to produce a single output, forming the basis of all digital computing. Common gates include AND, OR, NOT, NAND, and NOR. Mastering logic gates is essential for designing digital systems, from simple controllers to complex processors. Digital signals represent discrete values, typically 0 and 1, making them ideal for logic operations. Analog signals, in contrast, vary continuously over time and are used for representing real-world phenomena like temperature or sound. Understanding the distinction between digital and analog signals is key to interfacing sensors and designing mixed-signal embedded systems. Logic gates perform basic digital functions such as AND, OR, and NOT operations. These gates are combined to create more complex circuits, enabling decision-making and control in embedded systems. Understanding how to use and combine logic gates is fundamental for digital circuit design and troubleshooting. Pull-up and pull-down resistors are used to stabilize digital inputs, preventing floating states that can cause erratic behavior. By connecting inputs to a defined voltage level, these resistors ensure reliable operation of switches and sensors. Proper use of pull-up and pull-down resistors is essential for robust embedded system design. Mechanical switches often produce multiple signals or bounces when pressed or released. This can cause unintended multiple transitions in digital circuits. Debalancing techniques, both hardware and software, are used to ensure a single clean transition, improving the reliability of user inputs in embedded systems. Microcontrollers' block diagram typically includes the CPU, RAM, flash memory, and various I/O ports. This integrated design allows for compact and efficient control solutions. Understanding the block diagram helps you visualize how data flows within the MCU and how it interacts with external components. CPU is the brain of the microcontroller, executing instructions and managing data. RAM provides temporary storage for variables, while flash memory stores the program code. I/O ports connect the MCU to the outside world, enabling it to sense and control external devices. This combination makes microcontrollers versatile and powerful for embedded applications. Timers are essential for generating precise delays and counting events in embedded systems. Pulse width modulation (PWM) modules allow you to control the speed of motors or the brightness of LEDs by varying the duty cycle of a digital signal. Mastering timers and PWM is key to building responsive and interactive embedded applications. Analog to digital converters (ADC) enable microcontrollers to read analog signals such as temperature or light levels and convert them into digital values for processing. ADCs are crucial for interfacing with real-world sensors, allowing your embedded system to respond to environmental changes accurately and efficiently. Arduino and STM32 Nucleo boards are popular choices for embedded system development. Arduino offers simplicity and ease of use, making it ideal for beginners. STM32 Nucleo provides advanced features and higher performance for complex projects. Both platforms support a wide range of sensors and modules, enabling rapid prototyping and experimentation. Configuring GPIO pins as inputs or outputs is a fundamental task in embedded programming. Inputs allow the microcontroller to read signals from sensors or switches, while outputs control devices like LEDs or relays. Proper configuration ensures reliable communication between the MCU and external hardware. Timers are used to create precise delays and count events in embedded systems. They are essential for tasks like generating timeouts, measuring intervals, and scheduling periodic actions. Understanding how to configure and use timers is key to building reliable and responsive applications. Pulse width modulation (PWM) is a technique for controlling the power delivered to devices like motors and LEDs. By adjusting the duty cycle of a digital signal, you can vary motor speed or LED brightness smoothly. PWM is widely used in robotics, lighting, and motor control applications. Embedded systems often require immediate response to user interactions, such as button presses or sensor triggers. Efficient programming and hardware design ensure that the system reacts quickly and accurately, providing a seamless user experience. This responsiveness is critical in applications like industrial control and consumer electronics. UART is not limited to wired connections. It also enables wireless communication between devices. By connecting wireless modules like Bluetooth or Wi-Fi, microcontrollers can exchange data over the air. This capability is essential for modern IoT applications where devices need to communicate without physical connections. UART, I2C, and SPI are the three most common communication protocols in embedded systems. UART is simple and ideal for point-to-point connections. I2C supports multiple devices on the same bus, while SPI offers high-speed synchronous data transfer. Choosing the right protocol depends on your application's requirements for speed, complexity, and device count. Let's see how these concepts come together in a practical embedded project. By combining sensors, microcontrollers, and communication protocols, you can build systems that monitor, analyze, and respond to real-world conditions. This hands-on approach solidifies your understanding and prepares you for more advanced projects. This example showcases a development board connected to various sensors, demonstrating hardware integration in embedded systems. By wiring sensors to the microcontroller and programming the necessary logic, you can collect and process data in real time. This setup is typical in smart home, industrial, and IoT applications. Once data is captured from sensors, the microcontroller processes and analyzes it to make decisions or trigger actions. This real-time processing is essential for applications like environmental monitoring, automation, and safety systems. Efficient data handling ensures your system responds quickly and accurately to changing conditions. After processing sensor data, the microcontroller updates outputs in real time. This could mean adjusting a display, activating an alarm, or controlling a motor. Real-time output is crucial for interactive and responsive embedded systems, ensuring users receive immediate feedback and control. Developing embedded systems requires a blend of hardware and software skills. You need to understand electronics, programming, debugging, and system integration. Building these skills enables you to design, implement, and troubleshoot complex embedded projects, opening doors to careers in IoT, automation, and beyond. Throughout this video, we've explored the core concepts of microcontrollers, microprocessors, and embedded systems. From understanding hardware components to programming and integrating sensors, you now have a solid foundation. These skills are essential for building innovative solutions in today's connected world. To deepen your expertise, continue experimenting with development boards, sensors, and communication protocols. Explore advanced topics like real-time operating systems, wireless networking, and power management. The world of embedded systems is vast, and hands-on practice is the best way to master it. Leverage online resources, forums, and open-source communities to accelerate your learning. Platforms like Arduino and STM32 have active user bases, offering tutorials, libraries, and troubleshooting tips. Engaging with the community helps you solve problems faster and stay updated with the latest trends. Congratulations on completing this journey through microcontrollers, microprocessors, and embedded systems. With a solid understanding of hardware, programming, and integration, you're well equipped to tackle real-world projects. Continue exploring, building, and innovating. The future of technology is in your hands.